All right, so we're going to continue section 13.3. We're going to work some exercises. We are on page 844. We're going to start with number 8. It says in exercises 1 through 19, find the first partial derivatives of the function. Um, so they say first partial derivatives, and up to now I haven't mentioned anything but just partial derivative. I haven't used the term first partial derivative, but that indicates that we can take a second derivative, third derivative, depending upon the function, so forth and so on, the same way we had in calculus 1, where we could take the first derivative, second derivative, so forth and so on. So here they're just asking us to take the first partial derivative. And then when we get to a little bit later problems, I actually will introduce how to compute the second partial derivative. But if you know how to take a first partial, you know how to take a second partial, third partial, and so on. So the same way in calculus 1, if you know how to take the first derivative, you know how to take the second derivative, and so forth and so on. All right, so for number 8, they give us z equals the square root of 1/4 x squared minus y squared. All right, so, and we want to take the partial derivative of this with respect to x and the partial derivative of this with respect to y. So first, z sub x. Now, when you take the partial with respect to x, you treat y like it's a constant, and then you just take your derivative of this function with respect to x as you usually would. So if it's troublesome for you to keep in mind to treat y as a constant and avoid taking a derivative with respect to y, you can do something like this. You go off to the side and you just rewrite z. And this is not legitimate, but it may be useful. And just change your y term to something else, some number that doesn't appear in there at all. And then go through. Now, don't simplify anything here, because now I could simplify this and take the derivative a lot easier. But go through and take your derivative of this. Now you don't have to worry about accidentally taking a derivative with respect to y anywhere, but you have to keep in mind, do not simplify this. You have to use all the techniques that you would have used here. So here, first, in actuality, I would rewrite this. This is 1/4 x squared minus y squared to the 1/2. Now I want to take the partial with respect to x, but if I think I'm going to forget to treat y like a constant, I'm going to rewrite it this way, which is the same as 1/4 x squared minus 3 to the 1/2. And then you can take the derivative of that thing. And whatever you get right there, you will put that answer right here, but make sure you change those 3's back to whatever it was, y squared. So it might be better for you to just put the squared in there as well. So it's just, instead of treating y as a constant, you just change y to 3. Just when you get back and you put your final answer, change it back to y. Now, I'm not going to use this. I'm just going to go directly from here. But if what I do directly from here is confusing to you and you can't hang on to that treating y as a constant and you're going to accidentally take a derivative of this, then use this route instead. Go this way, and then at the end, switch it back. So I'll do it this way after I do it, coming directly from here. So taking the derivative of this with respect to x, treating y as a constant, I have to use the chain rule. So 1/2 times the inside stays exactly the same, 1/4 x squared minus y squared raised to the negative 1/2. Now times the derivative of the inside, but I'm taking the derivative of the inside with respect to x. So I'm taking the derivative of this term with respect to x minus, when I take the derivative of this with respect to x, I get 0 because I'm treating this like it's just a constant. So I'm not concerned about, I shouldn't have a 2y pop up here. So this is going to be times the derivative of the inside is just going to be 1/2 x. So times 1/2 x. So that's my answer right there. Now, if you opted to go this route where you said, I'm going to plug in a constant and do it that way and then come back and switch it, then you would say, okay, z sub x. Now I'm looking at this, but you have to maintain the fact that you have to use the chain rule. So like had you simplified and had you put a 0 right there and then simplified, then your answer wouldn't have come out correct. So that's why I said just stick something right there. Don't simplify anything. Just leave it as is. So even if you had put a -0 right there, you would just need to leave it and use the chain rule regardless, even though that thing is a perfect square. All right, so here 1/2 times, so bring that down. The inside stays exactly the same, 1/4 x squared minus 3 squared raised to the -1/2. Now this is the fact that you actually put in a constant is where this is where that would help. So now when you take the derivative of the inside, the derivative of this is going to be 1/2 x. The derivative of that is 0. So you'll get the same thing that we had here. You get times 1/2 x. So with some practice, even if you have to do this with some practice, hopefully you can get away from this. But if you do go this route, just at the end, that's your answer. Same as that answer. Just cross this stuff out, because that was just for your own personal use. But either way, you got the correct answer. All right, so now let's do the partial with respect to y. And as you do, after you've done a few of these problems, it becomes second nature. You just like differentiation did in Calculus 1. So now the partial with respect to y, you are welcome to go this route. You won't see me do that anymore unless somebody asks me specifically to do it in the problem session or something, but you're welcome to do that. That's perfectly fine. So now 1/2, the 1/2 comes down. The inside stays the same, 1/2 x, 1/4 x squared, minus y squared to the -1/2 times the derivative of the inside with respect to y. So I'm treating this like a constant. Its derivative then is 0, and then minus 2y. So times -2y. All right, and that's how we would compute that derivative. Now I'm going to go through these fairly slowly just because we're just learning them, but then we'll pick up the pace as we get further. All right, 10. W equals cosine, well, the same directions for 10 as we had for 8, because this is 1 through 19 have these directions. And they give us W equals cosine of U divided by V. All right, so I'll give you another technique here, and this one is just, this is a legitimate approach. It's not necessary though either. It's just to help if you think you may make a mistake along the way. So I know I need to find W sub U and W sub V. So those are the two different variables we have here. W is a function of U and V. So I'm going to rewrite this for my W sub U, and I'm going to rewrite this for my W sub V in two different ways, whatever's more useful for that one. So in to find W sub U, I'm treating V as a constant. So to keep that in mind, I would write this as cosine of 1 over V times U. Because when I'm going to find W sub U, this thing will be a constant, and I won't accidentally try to treat it otherwise because I put the constant in front of the variable. So when I'm going to take my partial with respect to V, U will be a constant. So I'm going to rewrite this as cosine of U times V to the -1, because that's the natural way. If I had to take a derivative with respect to the V, I would have my constant in front, and then that V, because it was the denominator, I would write it as V to the -1. All three of these are the exact same thing. So if you don't need to do this, don't. If you can keep in mind how to do it from there directly, then that's fine. But if you may get confused, rewrite it and put your constant in front the way we normally see things, and that may help you. So here, I rewrote this because I knew I was going to take my partial with respect to U on this side, and now I have my cosine of my constant times U, and I'm taking derivative of cosine of some constant times U. So now I know the constant's going to come out. Derivative of cosine is negative sine, and my constant is going to come out. So -1 over V times sine of, my inside is going to stay exactly the same, 1 over V times U, and then times, oh, I already did that, never mind. I was about to do the same thing again. So I have my constant came out, so my chain rule, I put it in the front instead of putting it in the back. My constant came out from taking the derivative of the inside of that thing. And then my derivative of the outside was negative sign, and my inside stayed exactly the same. All right, now over here, W sub V, I'm going to use this one. So now I'm going to take the derivative of the outside is going to give me negative sign of uv to the negative 1. That's going to stay exactly the same, and then times the derivative of the inside. So I'll do this one in that order, negative sign of uv to the negative 1. And remember, I'm taking derivative with respect to v. U is just some constant. So when I take the derivative of this inside part right here, the negative is going to come out to the front. And then I have negative uv to the negative 2. Times negative uv to the negative 2. All right, and that's what we would get there. So again, you can jump from here to that, and that's perfectly fine. If you need to put whatever you're going to treat as a constant in the front, it's perfectly okay to rewrite the things so that you see that constants in the front, so you keep in mind what's your constant and what is your independent variable in that situation. All right, so next we would look at number 22. All right, so number 22 says, number 22, so the next exercise is 20 through 25. Find the first partial derivatives of f at the given point. All right, so notice for numbers 8 and 10 that after we found our partial derivatives, we still had a function. So W sub u is still a function of u and v. W sub v is still a function of u and v. So we can still plug in points there. So now what they're asking us to do for 22 is to take our partial, and then after we take our partial, plug in whatever point they ask us to evaluate our partial derivatives at. So we're given f of x, y, z. F of x, y, z equals x, y squared times sine of z. X, y squared times sine of z. And they give us the point is negative 1, 2, 0. All right, so they want us to compute our first partials at this point. So first, let's do the partial of f with respect to x. So the partial of f with respect to x is so this is the first time we've seen a function of 3 variables in taking partial derivatives. When I take the partial of f with respect to x, that means not only do I treat y as a constant, I also treat z as a constant as well. So everything that is not an x is a constant. Every variable that's not an x is a constant. So that tells me this is a constant. This y squared sine of z, that whole thing's a constant. So I have the derivative of a constant times x is just the constant. All right, so y squared times sine of z is what we would get there. So the derivative of a constant times x, and this is why sometimes it's more useful to like switch the order of things and rewrite it, because we're used to seeing 3 times x, and the derivative of that is 3. This is our quote unquote 3, that y squared sine z. So now we're supposed to evaluate this at that point, because this is still a function of x, y, and z. There are no x's show up in here though. So f sub x of negative 1, 2, 0 is, so we're just putting in 2 for our y and 0 for our z. So we're just going to get 0 there. All right, and then f sub y. For f sub y, we're treating x and z as constants. So this is like x times sine of z times y squared. So a constant times y squared. When we take that derivative, the 2 comes down, gets multiplied by the constant, and then y, and then raised to the first power. So we're going to have, this is 2x sine of z times y. I mean, normally we would put that y right there, but just so you can kind of see the way that we would write it if we were just taking a regular derivative, I put the y at the back. All right, so now f sub y at that point, -1, 2, 0. So we put in x equals -1. We're putting in 0 for z again. So we're just going to get 0 there as well. And the partial of f with respect to z. So now we're treating x and y as constants. So this is some constant times sine of z, and we're taking that derivative. So constant multiple row tells us the constant is not going anywhere. So we leave that there. And then the derivative of sine of z is cosine of z. And now we're doing f sub z at -1, 2, 0. So our x, -1, our y, going to give us 4, so we get -4, and then times cosine of 0, which is 1. So we're just going to get -4 there. All right. So I'll stop this video here, and then we'll continue the next video doing some more examples from section 13.3.